Thanks everyone for joining our webinar on flexible AC transmission systems today. I am Hassan Zahir, Chief Commercial Officer at Power Technology Research. With me today, we have three speakers from the industry who have years and years of experience in this market, starting with Pedro Esteban, who's the Director of Asia Pacific for Metis Power, followed by Ralph Morgenstern, who's the Senior Sales Manager of Grid Stabilization at Siemens Energy. And then lastly, Kutub Beg, who's the Senior Analyst and leads the Power Electronics team at Power Technology Research. I would like to start today with a very brief overview of Power Technology Research for those of you who do not already know. Power Technology Research is a specialized market research firm focusing on power grid and new energy equipment research. We basically help our clients in the energy sector with quantitative and qualitative information that supports their strategic decision-making around business development. Within the power grid sector, we are covering everything inside and outside of substation, from transformers and switchgear to HVDC systems and flexible AC transmission systems that we'll talk about today. In addition to that, also focusing on topics like port electrification, substation automation, and power factor correction. On the new energy side, we are looking at equipment which is interacting with the grid. For example, EV charging infrastructure, energy storage, hydrogen as a power vector, so on and so forth. With that said, moving on to today's topic. With more and more renewables being integrated into the grid today, and a future where we expect most of our electricity demands being fulfilled by renewable energy, we expect the flexible AC transmission systems to play an extremely crucial role in grid stability. In today's webinar, we want to focus on SVCs and STATCOM, first from an application perspective and then from a demand perspective. We'll start with Pedro focusing on medium voltage STATCOMs and hybrid STATCOMs and their applications, especially in the industrial sector. Then we will move on to Ralph focusing on high voltage or utility scale STATCOMs. And then all of this will be followed by Kutub, who will give a regional and global overview of flexible AC transmission systems market. We expect to complete that in the next 45 to 50 minutes, and then we'll have a 10 minutes audience Q&A session. With that said, Pedro, over to you to share your screen and start your presentation.
Okay, I'll first share my screen.
Yeah.
Let me see how's it going. Sharing the screen now.
Yeah, we can see it.
You can see well?
Yeah.
And you can hear me well? Perfect.
Yes.
Okay. So anyways, thank you all. Thank you, Hassan, Kotap, and all the team at PTR for organizing this event and giving me opportunity to present in here today. I will just go through my presentation. It's a brief overview on medium voltage STATCOMs and hybrid STATCOMs. And I will have at the end of my presentation some application examples of those. So introduction first, briefly. This is the way we see the modern electric power system today. There are some end users involved with the generation of electricity or with the transport of that electricity. And then we have the different types of end users in the electric power system. We can also consider them loads or consumers in the electric power system. So what are the requirements from all of these end users nowadays? So anyways, we can classify them briefly in 4 different areas. Some of the requirements nowadays, very important requirements, are for power quality improvement. Some things are more common or well known nowadays: harmonics, interharmonics, unbalance, flicker. Some other things are becoming more important in the electric power system nowadays that they have to be taken care of. Second type of requirements, many of these end users, they require some ancillary services. Because here we are talking more about medium and high voltage installations, generation, and some big industries, for example, frequency support, voltage support, system restoration support, and some other ancillary services. All in all, as you have been hearing the term grid core compliance involve all these things. And then also nowadays it's very important the development of clean energy. This can be done by renewable energy integration, energy efficiency improvement. Also, end users have a lot of requirements on this area. And affordable energy access development also by energy supply management or energy demand management. Okay, this could be, okay, we can think about these things as sustainable energy management. So what I'm talking today a little bit shortly is the different kind of solutions that can be to take care of these requirements from the different types of end users. And one of the solutions that can take care of a lot of these things, of course, not all of these things, are power electronics based shunt compensation devices. These compensation devices, they don't have, let's say, energy storage. It will be discussed about energy storage-based devices like battery storage systems and so on. They have a lot of common points with these devices. But in this case, these devices don't have an energy storage. We can classify them in two groups, depending if they use low voltage or high voltage power electronic switches. And today I will be discussing and presenting some examples about IGBT switch IGBT switch compensation devices. Also, they can be called static compensators. Two types: STATCOMs and hybrid STATCOMs. These devices are pretty flexible because here you can see how we can connect them in the high voltage electric power system. Depending, of course, on the manufacturer and the design, they can be connected directly in this voltage range. If we use like IGBTs between 2 kilovolts, 3 kilovolts, we can also connect them directly up to 36 kV, or we can connect them with a step-up transformer almost to any kind of a voltage level. An important thing is that these devices, they are always connected in parallel with equipment that is causing problems, power quality issues, or we need to provide some ancillary services too. So the connection is always in parallel with these devices, with this equipment. If we move to STATCOMs and hybrid STATCOMs, some brief overview of what they are. This slide just shows the functions. This is related to the slide I was showing at the beginning. STATCOMs and hybrid STATCOMs, depending on the control system design and the use of these devices for the application, they can take care of a lot of different things for customers, improving the power quality of installations. They can provide certain ancillary services, and they can help with the development of clean energy by improving, for example, the energy efficiency of the installations, power factor correction, power transfer capacity increase, and so on. Also, they are very flexible from the point of view of applications. They can be used for renewable generation. Typical application I will show later could be solar power plants, wind farms. Ralph will talk later about the transmission distribution applications in high voltage. Any kind of installation or big installation that has fast changing reactive power demand, or loads that they are very dynamic. Those also have very good application for STATCOMs. It can be used also even for compensating the startup of large motors, railway electrification systems, and so on. How they are built, what is the design? So, as I mentioned before, depending on the manufacturer and the design, we can connect them directly into this voltage range up to 36 kV. Important thing here to notice, as I said before, they are connected in parallel with this equipment that generate the problems. So we need some measurements from the equipment, some measurements from the network, and the control system will be firing the IGBTs to inject in the system a certain current that will take care of the problems, or we will be able to provide the ancillary services needed. This is a STATCOM. The difference with a hybrid STATCOM is only that the hybrid STATCOM also will be having working together or controlled by this control system, mechanically, typically circuit breaker or contactor switch, or thyristor switch, capacitor bank, or reactor bank. If we want to connect this for these devices to higher voltages, over 36 kilovolts, the easier solution is to use a step-up transformer to connect there. We take the signals anyways from this voltage level. And again, hybrid STATCOM will be just having this kind of capacitor bank or reactor bank working together with the STATCOM modules. Components. Okay. If we do it very simply, STATCOM will have these components: a step-up transformer if needed, certain switch gear, and we'll have an active part where we'll have the modules. Cooling is very important, cooling these devices, usually liquid cooling, and control and protection system with the HMI. If we are thinking about a hybrid STATCOM, then we will have to add to these components whatever we will be needing for that certain application. Capacitor banks or reactor banks that they are switched with mechanically, or they are switched with thyristors. And if we are switching with thyristors, we will have also to control thyristor valves with this control system. In principle, also, I will not go too much into detail, but we have a control current source, and this current source is providing any kind of compensation current waveform in real time. So you can see here that this device, the STATCOM, can work in both sides, inductive and capacitive. It can provide these two currents. The difference with a lot of the conventional or passive solutions like capacitor banks and reactor banks would be that, an important difference is that these devices can still provide a very good output or even full output at lower voltages in the system. If we are thinking about a hybrid STATCOM, the only difference is the hybrid STATCOM will be adding a certain portion that you can see here in the capacitive side or in the inductive side. And there will be a certain speed on this a certain speed where we can use this extra portion, depending if we use mechanically switch devices or thyristor switch devices. That of course they will be providing a faster output to customers. If we are having a look to some application examples. So the first application here will be solar power plants. And one of the main problems that we have in solar power plants are solar inverters. So anyways, this is a very general diagram. The solar power plants can be built in many different ways, but the idea is that you have inverters there, and the inverters are connected together. You can have step-up transformers to connect to the substation voltage, 20 kV, 30 kV normally. And the problem of these inverters is that they are creating different kind of problems, power quality problems, and also many times, depending on the country and the grid code there, the owners or the operators of these solar power plants, they need to be able to provide certain ancillary services. So, for example, in this case, solar inverters, I think that they produce typically harmonics. So harmonic is always an issue. If you're operating also then the whole solar power plant, things that they are required many times is to have a certain voltage control capability there, reactive power control and power factor control, and also even fault right through capability. But as I said, these requirements depends many times on the topology, the installation, and the country where it's installed, and what is the grid code that is in use in there. So in this kind of cases, also this is a very simple example how a STATCOM could be connected in there. So we connect the STATCOM through a step-up transformer to the bus bar where the solar inverters are connected. So this will be basically located in the substation of the solar power plant, and we will have different kind of measurements from the different parts of the installation, and also very important from the point of common coupling, because basically we need to comply with these power quality requirements and grid code requirements in the point of common coupling where we are connecting to the main power grid, or where we are connecting to other users. So anyways, here are some example of typical values that customers are requiring. Very typical for harmonic mitigation is having a very low total harmonic distortion in current and voltage, to have a certain voltage control, 5 plus minus 5 to plus 10%, ability to control reactive power or giving reactive power support when needed, for the installations. Power factor is also important. Has to be closer to 1, of course, is always better. And some fall right through capability. Also, it's also a common requirement. Second example will be wind farms. And wind farms, we have actually two problems, two types of equipment, let's say, that cause the problem. One of them is the wind turbine generators. But also an important issue in wind farms is cables, because cables are capacitive and there are huge distances of cables in wind farms. So also they create certain problems. So from the wind turbine generators, you can see also that the harmonics that they are created, there can be issues with flicker, plus then we need to be able to control certain parameters of the operation of the whole wind farm. So in this case, hybrid STATCOM could be a good solution. I'll go to the next slide, because we have a part of the injection in the system comes in real time from the STATCOM device, but then we have capacitor banks and shunt reactors that they can provide extra inductive or capacitive reactive power to installation, but in a way that is cheaper, because it doesn't need to be produced by the STATCOM. But anyways, the capacitor banks, the reactors are controlled by the same control and protection system. So here also some kind of typical values, again, for harmonics, flicker, less than 1, PST, voltage control, reactive power control, fall right through. This is important in wind farm applications. Next example, mining. Also, mining is a very interesting area for STATCOMs. There are a lot of applications in mines, because mines have a lot of heavy machinery working there. In mines, we have variable speed drives, soft starters, we have very big motors, and also we have cable networks through the mine. So all of these things create also power quality issues. And these power quality issues can be affecting a lot to the equipment that we have within the mine. And if the mine operations are pretty big, we need to be able to comply with the grid code regulations of this of the certain country in the point of common coupling with the main network. So in this case, typical things, harmonics mitigation, because variable speed drives, especially these big ones, they generate a lot of harmonics during the operation. There can be flicker, because we have all these dynamic loads they are operating. Power factor also can be very low in these installations. And when we improve the power factor, that means also a lot of savings these customers can be getting, because they need to get less apparent power or less power from the electrical utility to anyways to do the operations in the mine. So in this case, as you can see again, very similar always the idea of the connection of these kind of devices. We will be connecting this device somewhere in the medium voltage in the installation, typically in the substation of the mine. And in this case, we can use a STATCOM to provide the dynamic output in real time, plus a couple of capacitor banks that we will be working together with the STATCOM, so we can provide extra capacitive reactive power cheaply. So anyways, again, some typical values what are required for these applications. Target power factor, of course, 1 is good to reduce the energy cost of the operations in the mine. And finally, another application example in medium voltage will be railway electrification systems. Railway electrification systems, they have two issues in here. We have one of the issues will be harmonics, because of the rectifiers that they go in the locomotives, in the trains. And the second issue will be here load balancing. This is a big thing, because you see in this kind of a diagram a typical connection of this railway electrification system. So we are taking power from 2 phases in a 3-phase system. That means that we are creating unbalance. When the train is passing through the substation or where we are located, there will be an imbalance created because of this connection. So this imbalance will be affecting other loads that we might have there, that they are 3-phase loads, and also they could be affecting any other users that we have in the same kind of system. So solution for this also could be a STATCOM. And a STATCOM, okay, in this case, the whole output needs to be provided, or the current needs to be provided in real time, so we can take care of harmonics and an imbalance in the moment that the train is going through this kind of area of the railway. In this case, okay, harmonics, very standard values to mitigate, and typically customers asking imbalance in the current and imbalance in the voltage being less than 2%. So there will be not any issues created to the other loads that we have in the system. This was my presentation for today. I don't know if I went a little bit over time, but anyways, I think I covered all the topics I wanted to cover today.
Thank you, Pedro, so much. I would just like to iterate to all the audience that if you have any questions, please already type those in the chat as well, and then we'll make sure we address them in the Q&A session. And once again, thank you, Pedro. And with that said, Ralph, over to you to please share your screen and start your presentation.
Thank you.
Yes. Good morning. Thank you. Let me share my presentation. I hope you can all see it well.
Yeah, we can see it now.
Give me 1 second, please. Arrange the screen. Okay. Put here and that's that. Yeah. Okay. Hello, all together. Thank you for your time. My name is Ralf Morgenstern. I'm working with Siemens Energy in Germany, in Erlangen, and I'm in the technical sales team for grid stabilization solutions. The question is clean energy transition possible without facts? I would clearly say no. There's various reasons, and let's talk about the issue, what can be done and what are we facing today. There's different items I would say influencing the whole grid nowadays. On one side, we have the decarbonization, means big power plants are shut down and are replaced with, let's say, renewable energies like wind, solar, or whatsoever. So there's a big change in the grid. The decentralization, followed by that, like have wind farms everywhere, have solar farms everywhere, will result in a change of the grid, where we had previously, let's say, some huge power plants on certain nodes. Now we have small power producers feeding into the grid at different locations. So we have to manage the grid to be capable to get all the energy into the grid, what is produced. The deregulation, what is happening, is also changing the whole situation. In my world, in our world, where we have mainly TSOs as our customers, mainly a regulated market, now we have more and more IPPs where they can make use of different models, and they have simply different requirements. And there is different business models applied, energy trading and so on, and different services which allow different solutions into the grid. But as we want to talk about facts today, what is facts about? I mean, facts actually, it's flexible AC transmission solutions, and mainly they are used for support the grid voltage by using reactive power. We balance the reactive power to get rid of maybe negative phase sequence, as said before by Pedro, for load balancers. And also facts devices will provide short circuit power and inertia, different technologies available. And it's the task for the grid operator to select the right tools to manage their grid by to get rid of voltage instability, to balance the grid, and to provide short-circuit power and inertia as the main drivers. For the utilities, important things are, let's say, the increase of the power transfer capacity. So you want to utilize your system as much as possible. Instead of building new lines, you make sure you use the lines in an optimal way. You want certainly support the integration of renewables. There should not be any stoppers where we have a line or a node where you say it's simply not possible to get more renewable on board because it's at the limit already. You need to get the long lines stable. You don't want to risk an unstable grid by feeding in more power or do not manage the stability in the right way. And by doing so, you have the grid stable. You want to transmit active power. And of course, the whole thing, what we are doing here, we want to, by any means, avoid any blackout. And these FACTS devices, they can help to avoid it. Not saying it will stop it, but it will certainly help to avoid. If you talk about the industry where FACTS devices are used, I mean, some example is you want to have the production process stable. You don't want to get any interruption by instability of the grid. You want to get the grid in a way that the technical parameters are met. Otherwise, there is some penalties applied. And for example, flicker reduction is an issue, for example, for steel plants, and you want to get rid of them. Some main technologies for FACTS which are used. We have the classic SVCs, we have the STATCOMs, there's the series compensation, there's the synchronous condensers, there's mechanical switch devices. And for each of the technology, we can talk hours and explain, but as today, we want to concentrate on the STATCOM, which is, I would say, a very flexible device in the FACTS family. And yeah, we will look on this under some slides later, what's about it. Additionally, from the FACTS devices, we would have SVC plus frequency stabilizer. SVC plus, that's the Siemens term for a STATCOM. So the SVC plus frequency stabilizer would use ultracapacitors to provide frequency stability. We would have the mobile STATCOM. We will talk later about it more. And we have also a UPFC plus, which is a unified power flow controller. It's a series device to control the load flow in the system. But as said, we want to focus on the STATCOM today. The STATCOM, very simplified in a single line diagram. We connect it to the high voltage grid, whatever voltage it is. We will connect it through a circuit breaker. And normally we would use a step-up transformer. If the voltage is lower and the medium voltage, we might connect it without. But in our cases, let's say on the high voltage grid, normally we would use a step-up transformer. And we have a medium voltage bus where we have the STATCOM itself, where we have the converter. We have a phase reactor in between. And of course, there's a control system to manage all that. And most of the cases, or normally, it will collect the data, the values from the HV grid, and will control it against that. How does it work? The converter itself, we are using IGBTs. We use a number of IGBTs, which are controlled individually. And each of this submodule will have, or this module will have a DC capacitor with a certain voltage. And by switching those IGBTs, we can sum up the DC voltage and we can generate this nice little sinusoidal wave. And we can see the steps are quite small. And this is to make sure you will not apply more harmonics into the system, or at least keep it to a minimum. There is a redundancy inbuilt. So if one module would fail, it will be bypassed and you will continue operation. You get an alarm, you can replace the module during the next shutdown, but you will not trip the system. So for the availability of the system, that's a very good measure to maximize the availability of the system. For the performance of the system, it is quite important to understand a bit the way the control works. And as we said, let me go back, we control on the high voltage grid. And if the voltage of the grid would, for example, have a drop, will go down, it will be detected. And then you would apply a voltage to the converter and feed in to bring up the voltage where it was. But this will depend very much on the strength of the system. So if you have a very strong system, you need more power. Compared to a weak system, to a weak grid, you need less power. Otherwise, you might end up, if you have the same parameters applied, if the grid would be strong, you would have a massive overshoot, which we don't want. Or the other way around, if you would assume there is a weak grid, a strong grid, and you apply less power from the converter, you would be very slow. So in other words, you want to optimize the speed of response and the minimum of overshoot. But as this is depending on the grid, we do a measurement of the strength of the grid on a regular basis. Depending on the customer requirements, you do it every hour, every 2 hours, you measure the system strength, and then you will adapt the settings or the parameters in the control system to minimize the overshoot and to reduce the response time. Some typical values would be the response time, it is 1 or 2 cycles, and we want to have the overshoot below 10%. And then there is a settling time, and you want to reduce this also, and we say after 100 milliseconds, the settling time is done. The settling is done. If we have a look how such a converter would look like, we have the IGBT modules. We have the power module with the DC capacitors. And if we put all those in series, we can see the 3 phases here. Or we have the full converter connected, 2 converters in parallel, or they're connected in the back. So it means it is 1 row in series. This is how we can build it, the SVC Plus. If we have a look on the typical configuration of a system, we can see here there's the power transformer. In this case, it's a 3-phase transformer. It could be 3 single-phase transformers. It is connected on the MV bus. We have the phase reactors. These are air core reactors. Just to have them optimized, the most economic one would be the air core reactors. We have the building. We can see the converter itself here with the IGBTs. The IGBTs, they're all water cooled. So there is a cooling system here to bring the cooling water to the IGBTs. There's the outdoor cooler. There's the heat exchanger. And of course, there's the control room, which takes care of the control of the system with the protection equipment, with the SCADA system, whatever is needed to remotely operate such a STATCOM. Of course, it is unmanned station. It will operate fully automated from the control room of our customers, and you can dial in, you can make the necessary adjustments for the parameter of the system. You can choose different operating points, different operating modes, but this would be far too much to discuss in this meeting here. And of course, there is a roof. Here it's just not shown that we can have a little bit of look inside the building. The area here, it will be fenced off. There's an interlocking system that you will not touch the live parts. The same thing is in the converter room, where we make sure you will not be able to enter the room if the whole system is live. So the SVC Plus, that is the Siemens Energy's term for a STATCOM. You can say it here. A nice functionality, what is really must to mention, what it does provide by using these modern IGBTs, we do have the active filter functionality. You can actively filter up to 4 different harmonics out of the system. It will automatically detect which harmonic is most affected, and it will optimize their parameters to filter those harmonics. The STATCOM itself, it has an excellent under and over voltage behavior. It's a voltage source converter, so it's not depending on the voltage on the HV grid that much, and can still provide the necessary reactive power more or less independent from the grid. There is different configurations available. We do have it here. We call it open rack. So it's in a building. There is the converter, the control room, and we do have a containerized version as well. We're using single phase containers for bigger applications, using a 3-phase container for smaller applications. It depends on the requirements. Normally, our customers will tell us the size of the STATCOM, and it is for us to decide which would be the most suitable one, open rack or containerized, single phase or 3-phase containers. There is a long experience for FACTS devices in our house, more than 30 years with FACTS technologies. We can make use of this experience to continuously optimize our solutions. And what is also a very big benefit of this SVC Plus of the STATCOMs, there is a high amount of independency from the grid, which provides a very high flexibility if the grid will change at a later stage. I've mentioned it before. We have the mobile STATCOM as well. It's the 3-phase container, in this case mobile. You could have the GIS also on a trailer. We can have the transformer on a trailer. And we have the SVC Plus container, the STATCOM, with the outdoor cooler. We have the phase reactors in a container, and we have an auxiliary container. It's in a full mobile configuration. It can be used for temporary uses, or if you have issues with, let's say, the deploy time of the delivery time of such a system, you're very flexible if you have this one somewhere parked. And it can be brought from one site to another one. As it is done, we can see a nice picture here. There is a mobile STATCOMs in operation, and we have experience with this also already. That's it from my side. I hope I am in time. I think there is the chance for questions later on. Feel free to ask the questions or to get in contact with us at a later stage. Thank you.
Thank you so much, Ralph. I already see some questions in the chat as well. We'll get to them after Kutab's presentation. Kutab, over to you then to please share your screen and then start presenting.
Hey, let me know when my screen is up.
Yeah, I can see it.
Okay, perfect. First of all, good morning and good afternoon, everyone. And thank you, Hassan. Uh, First of all, I would like to thank and appreciate Pedro and Raf for their presentations and explaining the functionality and applications of medium voltage and utility scale STATCOMs, and especially the mobile STATCOMs. Um, I think the knowledge and information shared by both the panelists is very interesting, and it clearly indicates that the importance of FACTS utility to ensure this whole security of supply in power grid sector is crucial, very crucial. They have set the stage really well for me to talk about other non-technical slash business aspects of the technology. Um, so before jumping into the today's topic, I wanted to give you all a brief background of how we have put together this information we are going to present. So first of all, today we are going to talk about the facts market. And as Raf and Pedro both have mentioned that in grand scheme of things, there are several technologies which are part of facts, but at the moment we are going to talk about SVCs and STATCOMs from a statistical standpoint. Um, I think in terms of technology, both of these panelists have explained it very well. I will be primarily focusing on covering this topic from more of a business standpoint. So the information I'm about to present is basically the extracts from our fact service. We have been covering the demand landscape of facts market for quite some time now, and of course, it comes with a contribution, a continuous contribution and input from industry experts like Raf and Pedro. Um, so first of all, I want to talk about the global trends, that what has happening globally in the FACS market or SVC and STATCOM market. Um, so talking about the historical landscape of facts, especially talking about the last year, the last 5 years, you can see that in 2021, we saw facts about more than 20,000 megavolt ampere active of facts commissioned around the world. Uh, Overall, when we talk about every fact technology, including STATCOM, series compensation, SVCs, synchronous condensers, between this time span of last 5 years, about close to 50% of these technologies were STATCOMs, which did not used to be the case in the previous decades. Of course, it's a new technology, but it has gotten a lot of traction in the last 1 decade. 30% of these were series compensation devices, and SVs and synchronous condensers were followed by 16 and 17% of the installations during that period. In terms of application standpoint, 80% of these devices which were basically deployed between the last 5 years went into the utilities. 12% went into the renewables. Of course, we've seen a huge rollout of renewables. And when we talk about grid integration, and as both Pedro and Raf has mentioned, that we have to comply with the grid codes requirements, grid interconnection requirements, and there are several other things. And for that, we require these kind of devices. Rest of the 8% went into the industry. So, and when we talk about an industry, we are talking about energy intensive industries like steel plants, industries which are, let's say, far away in remote areas like mining. We've talked about railway as well. ONG, a very not a major market, but yes, few of the systems. So this is the overall application and technology split and the overall landscape effects, which what happened in the last 5 years. I wanted to discuss that how the industries or how the renewables utilities drive this facts market. For example, since the key focus of this today's topic is on renewables, I wanted to discuss this. Is renewables directly driving this market? Or is it because of, let's say, grid codes or regulations, things like that, even for the utilities who are deploying renewables or who are probably integrating renewables with from the demand centers, from the generation centers towards the load centers. For industries, typically there are power quality requirements, grid compliance. They have to make sure that they're not polluting the network with their energy intensive equipment. So this is how basically this is the main reason behind their FACTS deployment. But for the grid side, it's not just the grid regulations or grid codes which makes these utilities, or let's say renewable energy developers, to deploy the FACTS devices, but beyond these requirements, we have seen a massive deployment, and the clear evidence for that is that we have seen a lot of SVCs, series compensation systems, and since we have seen the STATCOMs coming into the market, we have seen a lot of these devices becoming part of the grid. So it's a direct relation as well between the renewables, and it's an indirect relation as well when we talk about FACTS market. Uh, I wanted to share another very interesting insight that how renewables have been driving this market. So this is a graph where we can see that we are talking about SVCs, we're talking about STATCOMs growth, and we're also talking about renewables growth. And this dotted line basically shows the renewables, this SVCs, this shows the SVCs, and this is the curve which shows STATCOM growth. Here you can clearly see that till 2000, of course, STATCOM did not used to exist. We saw a lot of SVCs deployments. Between 2000 and 2010, we saw STATCOMs coming into the market. They were very slowly gaining traction, and the reason was that they were faster. They had a smaller footprint as compared to SVCs. But of course, we just like energy storage systems, we saw a very huge difference between their prices earlier. But since we saw takeoff of renewables in the global market, and especially wind and solar, we saw this STATCOM market also took a major turn. And because of that, we saw a lot of STATCOMs being deployed as well, and we have clear evidences for that. Since we have been covering a lot of project specific information globally, we saw a lot of wind farms development in Europe, and with several of these wind farms, either for the evacuation of energy, they were using HVDC, which is a relatively tricky process or the projects, because of all of the right of the way, several approvals are required, and several other things are involved when we're talking about HVDC deployment. But from the FACTS devices standpoint, if we have to just evacuate that power from AC, HV, high voltage AC, FACTS were deployed with those systems. So we saw a lot of wind farms deployment across Europe, especially in UK, and with all of those systems, we saw a lot of STATCOMs being deployed. So you can see that after 2010, as we saw a takeoff in the growth of renewables, we saw a major takeoff in the demand of the STATCOMs as well. So this is the global landscape I wanted to discuss and talk about. I also wanted to discuss that how this STATCOM and SVC market has been formed in different regions. We have divided it into 4 regions primarily. We are talking first, we are talking about Europe, then we are going to talk about Americas, then we are going to talk about APAC, including China, and then we are going to talk about Middle East. So in Europe, it's one of the key demand centers globally when we talk about FACTS market. As I said earlier, because of an unprecedented growth in offshore wind sector and overall renewable sector, we saw a major growth in STATCOM, especially for in UK in the last one decade, from 2010 to till 2021, and it's still ongoing. We saw a major growth in demand of STATCOM market because of the grid requirements. Earlier, it was in the recent years, we have seen Germany to be emerging as one of the key markets for FACTS. I was basically looking at the transmission development plans by Federal Network Energy Agency of Germany, where all the TSOs cumulative have plans to deploy more than 70 STATCOMs, which means a very huge investments in these kind of systems. Of course, Germany has plans to reach their clean electrification goals much more earlier than several other countries. And if they want to stay on track in terms of those plans, and if they want to make sure that grid remains stable and fit for all these renewables, fit for to handle all these renewables, of course they are going to all these STATCOMs. Other than that, we have other markets like Norway, France, Sweden. In Sweden, there was another interesting thing which happened, which also Raf mentioned, that closure or phasing out of conventional power plants is also making the grid operators to install STATCOMs. There, of course, there are other technologies as well, like synchronous condensers are coming in. But yes, one of the key technologies which a lot of these countries are focusing on is STATCOM. We have seen that in Sweden as well. We have an example of a closure of a nuclear power plant. In Norway, we are still looking at a few SVCs refurbishments. We are also looking at new additions of STATCOMs. In fact, one of the largest capacity STATCOM within Norway was installed in 2021. In terms of application split, again, you can see that most of this technology is serving either the utilities or the renewables primarily. I would like to mention one more thing here, or clarify one more thing here, is that sometimes these STATCOMs are bought and deployed, or procured and deployed by the renewable energy developers. Sometimes these renewable energy developers are big utilities themselves. So they are also looking after they're also the TSOs, they're also the developers. So let's say if they're also developing an offshore wind farm, so of course that market would be reflected in the utility sector. But if there's just a renewable energy developer, which is not into the transmission side of the things, but just a generation sector, of course, that would be reflected in the renewable sector. So that's what's happening here. Coming towards Americas, again, one of the second key markets globally when we talk about FACTS deployment. In fact, one of the pioneers as well. When we talk about series compensation, series capacitors, one of the first systems was installed in USA back in 1930s or I believe 40s. So a very, very old and mature market in terms of FACTS deployment. Second market in America is Brazil. We've seen a lot of deployments there. When we talk about FACTS, again, you can see that when we talk about this overall market in the last 10 years, you can see that after 2019, there's a huge jump in 2021, and that is because of that COVID restrictions. There were a lot of projects which were delayed because of COVID, and all of those are basically commissioned or completed in 2021. That is why you see a huge peak here in 2021. In terms of the application split, again, it stays the same. USA, and especially in USA, we have the investor-owned utilities, the major basically buyers or users of these STATCOM technologies. That is why, again, you see a lot of happening in utility sector. Second major demand center within Americas is the steel sector. US steel market is one of the key markets globally, and because most of these are run on electric arc furnaces, we require power quality equipment like STATCOMs or SVCs, for these kind of applications. So yes, you've seen a lot of, we see a very significant share of industry in US as well. Especially if we talk about Canada, there's not a very mature market of steel, but yeah, we see a lot of small scale STATCOMs going into the mining sector of the things. Another thing I would like to mention here is that you see a 4%, which is a very small chunk, which is going into the renewables at the moment. That is because earlier we did not see a very unprecedented growth, especially in the offshore wind sector of the US. Now, since the new administration has come in and they have changed their policy towards offshore wind, we see a very rapid and a very strong demand for not just STATCOMs, but also for synchronous condensers and also for the HVDC systems. So in future years, if I had to forecast the application split of renewables from 2020 to 2030, this is definitely going to be a double-digit growth. This is what we expect as a market observer in Americas, and especially because of the US market. Coming to the APAC, so this market at the moment includes China. The analysis at the moment you can see here on the slides. And there's a very interesting thing that is a low voltage solutions. We have seen a huge deployment of static wall generators in China as well, in renewables and in industries. And typically, when we look at the Chinese market, we have to also incorporate the demand of SVGs as well, because several sectors are being served by SVGs in China because of these systems. They are relatively, I believe, cheaper in price, readily available, uh, and available in the form of cabinets and things like that. So naturally, it's easier for them to deploy them, easier for them to even procure them. That is why you see you know peaks in APAC sector. Other important markets in APAC are India, South Korea, Australia. Uh, when we talk about India, in the last 5 years, India has done massive investments in STATCOM. They have deployed more than 8 to 9 systems. I believe Siemens Energy itself is one of the partners to support PGCIL, Power Grid Corporation of India Limited. They have supplied several systems recently. Just like that, as similarly in Australia, in South Korea, we have seen a lot of deployments. Australia itself is a very key market for facts. In South Korea, it's not just a key market, but a couple of global players or regional players are also emerging from South Korean market. So there are several players from competitive landscape, and they're part of it, and they're basically part of this regional market. Coming to the Middle East and Africa market, here you can see that only a handful of additions in last few years, because of the reasons that T&D market itself was not very strong since 2015, and then COVID happened. But now the way we see this market is that we are expecting huge deployments of STATCOMs, especially from the key market, which is the KSA. So of course, you can see that the market in so far till 2021 is not very strong, but we are expecting that Saudi Arabia is going to recover this market very soon. In fact, we have a visibility over a couple of thousands of megavolt ampere reactive projects in coming years. So one of the relatively not very strong market as compared to the rest of the regions. Coming to the future landscape, this is just a very high level overview that what's going to happen in future. Globally, you can see that in terms of overall growth, there's a very strong CAGR till 2027, because we're looking at the 5 years of the market, and you can see that both of these markets are going to grow. But in terms of if we look at these technologies separately, the growth of STATCOM is going to be more, and eventually they are going to replace SVCs. In terms of regional split, right now you can see that we have a major share in China at the moment. Here we have split China, we have segmented China separately. But in future years, you can see that for Americas, this split is going to increase a lot, of course, because of a lot of renewables coming in. In APAC, this split is declining a little. Reason is because of there are other devices available like energy storage systems as well, which will be replacing this market. Because they have the same functionalities. So yeah, that's what's happening overall. In terms of overall technology alternatives which we have available are the battery energy storage systems and synchronous condensers. And I've been looking at several studies where they both seem to have a very strong potential for, at some point in time replacing these STATCOMs as well. So yeah, that's pretty much it from my side. Feel free to post any questions you have regarding the market. Thank you very much, everyone.
Thank you so much, Kutab. I see that there is already some questions in the chart as well. Maybe we can start with the first question, where it talks about, the discussion encapsulates facts in the utility in power grid, with several other technologies available to maintain power quality, such as harmonic filters. Are fax devices still going into the industries like steel sector? Maybe we can start with you, Pedro, on this one, and then we can follow it up with Ralph.
Okay. So anyways, yes, I think there's still demand in the industry for fax devices in the future also. Industry, we can understand it like steel mills, rolling mills, mines, and any kind of like a industry that is handling big loads or very fast changing loads. So harmonic filters, passive harmonic filters also is a solution for these in these kind of cases, but basically for the harmonic filtering. What the thing that the FACTS or STATCOMs bring to these kind of applications in industry is also the control of the reactive power, the improve of the power factor, balancing the loads, mitigating flicker, and so many other things that passive harmonic filters just cannot do. Anyways, also STATCOMs have the possibility to filter a certain degree of harmonics. Usually STATCOMs can filter up to 25th harmonic and so on, the most present in the industry. So I mean, passive harmonic filters will not be a replacement for these kind of STATCOMs. And I think anyways, passive harmonic filters or these passive solutions, somehow they might be, the use might be decreased in the future if the prices of these power electronic devices are continue decreasing.
Thank you. Ralph, Kutab, would you like to add something to that?
Well, I think most is said. Just as a fact, a STATCOM is a highly dynamic device offering lots of good services, and it can be used. It's the decision of our customers whether they want to consider or not. It's we as the OEM, we can provide the technology. If it's applied, it's many times others people's decision. So I definitely see the advantage, as Pedro said. I mean, the harmonic filtering is one of the examples. Yeah.
Absolutely. Then I see a lot of questions. There was a very active chat. I'm very happy to see that have already been answered by you both. Thank you so much. There is an open question, which is, I think, more related to Kutab, which is there is a significant decline in the Middle Eastern market. Do you think this market is going to recover soon, considering the uptake of renewables in Middle East?
Yes, definitely. I think it's a well-noted point that we have seen a significant decline since overall the T&D market has seen a decline since 2015 in Middle East. Of course, before it could recover, COVID happened. And since then, we have seen a lot of delay in the projects. But I have visibility over several tenders, basic and when I just talking about their overall capacity, I think they're more than of 2,000 MWs. So yeah, we have the visibility over a lot of tenders in KSA, UAE, Bahrain, and definitely we would expect that these tenders would be commissioned, or these products would be commissioned by the end of 2022 or 2023. So this market is going to recover from this year end.
Okay, and then we have one more question. I think it's very similar to the question that Ralph already answered as well, which is with SVCs phasing out and synchronous condensers coming back to the market, how do you see the future of synchronous condenser in this market of facts? Maybe Ralph, if you want to comment on it again, and then any other panelists as well.
Well, there is certainly a renaissance with synchronous condensers. They can provide reactive power, not as dynamic as a STATCOM, but they can provide reactive. They will provide reactive power. Main purpose, I would say, is more for short circuit power and inertia. And then it's a question: what is the main focus on? Some grids only look on short circuit power, some others need inertia, and it's really depending on the topology of the grid operator or the grid, and how the grid operator tries to mitigate the issues. And there's different tools available, and then it's a question of optimizing in which direction. Yeah, what we see, there is a worldwide demand on synchronous condensers, which is increasing quite a lot.
Pedro, would you like to add something to that, or Kutab, you?
Well, I think from my side, not too much to add. I agree with Ralph, and of course, this is a synchronous condenser. He knows very well. It's in the product portfolio of Siemens, so they have also very long experience with these devices.
Just to add one thing here is that I think Raf has explained it very well already. So very good market indicator, and that's how we see it, that when we look at clean electrification goals by different countries, they are expanding all the way till 2050, 60. So which essentially means as they are going to continue to incorporate more and more renewables and going to phase out all the conventional power plants, which means coal and nuclear, definitely they are going to require more and more synchronous condensers. So it's a need that is going to be generated because of all of this phasing out of conventional power plants.
Thank you. And then I see a comment from Gaurav from Transco actually about reconfirming what you're saying about the Middle Eastern market, that there is already some STATCOMs underway, and then there's one being executed as well. Then there's a question, which is a very interesting question actually. Is there some research going on to add the possibility of inertia in fax devices like battery energy storage systems? I know, Kutub, we were talking about this some days ago. Maybe you want to start to answer that, and then Ralph and Petro, if you want to add to it.
Yes, I believe so. I believe Raf and Pedro would be able to comment on in more technical way, but I came across one very interesting study by NRELUS, National Renewable Energy Laboratory, and they were basically doing some research on it, and based on their findings, they think that yes, if we are going to use battery energy storage systems in conjunction with STATCOMs, that is something would be an ideal solution for to deal with almost all of the grid challenges. So that is something also under study. I'm sure Raf and Pedro can comment in a much better way.
Yeah, I mean, as part of our portfolio, we do have a SVC plus frequency stabilizer. And this one, it is a STATCOM, not using batteries. We are using supercapacitors. But the thing is, you need active power for frequency stabilization. And therefore, we are using the supercapacitors, which exactly provides the synthetic inertia, what is already mentioned here. Yeah.
Yep, in the same line, as you said, energy storage is needed in these kind of cases that we need synthetic inertia or virtual inertia. So battery storage is a good solution for this. So any kind of a power electronic device that can have some energy storage to provide that.
Perfect. So looking at the time, I think we need to call it a day. We're already 10 minutes over. I would like to thank you guys once again for your time with these really interesting and detailed presentations from a technical point of view, but then also bringing the market and the demand perspective, and then also for all the audience for attending. Thank you so much. And of course, the information and the slides would be available in a couple of weeks from now on the event website. And then from there, if you have any other questions, please feel free to follow up with us or with Ralph or Pedro directly, like based on your questions, which we have not been able to answer right now. Thank you so much.
Okay, thank you.
Okay.
Goodbye.
Thank you, everyone.
Thank you all.
Bye.
Bye.
Bye.